Hello, I'm Channa Bankapur from GoMaster Technologies. Today I'm going to discuss my solution to the LeetCode problem, best time to buy and sell stock, fourth. It's today's problem in the October LeetCoding challenge. And this problem is fourth in the series of problems. And all of them are interesting, so try to give it a try. And this is relatively harder than the other three. So let's see how does this problem look like. So we have an array of prices here. Prices are all prices of a given stock on some ith day. So there are like n days from day 1 to day n. And we need to come up with an algorithm to maximize the profit. So we have basically only k transactions to make, not more than k. It's at most k transaction. And a transaction is buying a stock on some day and selling the stock on some one of the days in the following days, right? And one more thing is we cannot overlap transactions. That means we can only once we buy a stock, we cannot buy another one until we sell this, right? So that's the restriction. So let's see how do we solve this one. Clearly, this is an optimization problem, and it's relatively harder problem. And let's start with the state space approach, and hopefully we land on an efficient algorithm using dynamic programming. So for my convenience, I'm gonna reverse the array. So when we have 0 to n minus 1. So normally these are all arranged in the day 1, day 2, and then day n order. I'm gonna reverse this one so that the last location is gonna have day ones, and then and so on. The first location, which is prices of 0, is gonna have nth days value, right? So this gives me some kind of convenience. Let's see how does it go. So the problem I want to solve, I'm going to call that as F. So the parameters that matter to me are K and N. So what is K here is we can make K transactions. That is what is allowed right now. And N is there are N days after this. So there are N days to actually go on. So to start with, yeah, the original F of K comma N is going to be given. But yeah, going forward, this is just a parameter. All right, so now let's see how does it look like. So we have these things. Let's see how do we partition these possibilities. So I'm just looking at this nth location. That nth location is going to be the first day, right? So on day 1, either I can buy or not buy. These are the only two options because I haven't bought, so I cannot sell. So there are two possibilities. One possibility is don't buy, or so if I don't buy, what happens, right? So and then another option is buy. So if I don't buy on this day, it's as good as solving the problem with the same number of k transactions allowed, but we have only n minus days left, right? Which is going to be the first n minus 1 values in that array of prices because I already reversed it, right? So if I buy on that day, what happens is I spend some money. So I'm going to call that as basically a loss for the moment. It is going to be minus of price of that nth element, which is like p of n minus 1. But we need to solve a different problem here because once I buy on that day, now I cannot buy another one, but I have now I need to figure out when to sell it. So that's not an f function, so I'm going to introduce a new function called g. So g still have k because we haven't even completed first transaction. K indicates the number of transactions we can do, we have the ability to do, and the number of days left out is n minus 1. So what is G function? G function, first of all, it is already holding a stock. We don't know what is the cost because that is already captured here. We don't have to care. So we need to sell that and then maybe solve the problem afterwards. So we have like n minus 1 days left, right? So this is for me the function f, and let's see how does function g look like. Suppose I'm gonna write g here itself. Suppose g looks like here, g of k comma n. I'm going to use these parameters again, k comma n. Obviously the actual nth day we are not going to have an option of selling at all, because the nth location is basically the first day, right? So in first day you cannot sell, you can only buy, but I'm using them as parameters here. But again, I have two possibilities here. One is either don't sell or sell, right? So what happens if I don't sell? So this is don't sell part. If I don't sell, then I have another left n minus 1 days left out. I can still sell later. So g of k comma n minus 1 is what we need to solve, right? What if we sell on this day? So if I sell on this day, I'm going to make some money, right? So that money, I'm going to call it as P of n minus 1, because that is the money we are going to get, right? So clearly, if you see from the previous one where I negated P of n minus 1, in this case, I'm adding that. So because whenever we sell, we make money, and whenever we buy, we kind of invest or lose money. So obviously, when we sell, we should sell for higher to make that profit. That difference is going to be the profit, right? So what we need to do after this, we have sold this one already in this day. Now we have to figure out how to solve the rest of the problem. So now we have made one transaction, one complete transaction, and now we are not holding on to any stock. So now it is back to that function f, right? Just that we have k minus 1 here because we have already completed one transaction, and we are left with the remaining n minus 1 days, right? So this is exactly what it looks like, right? So f of k minus 1 comma n minus 1 plus this p of n minus 1. So we need to solve these things. And base cases are very simple. I don't want to get into details. If either k is 0 or n is 0, the value is going to be 0 for both f and g, right? So we can go with that. And let me directly implement this. But yeah, I don't want to implement naively whatever the recurrence I'm getting here. Uh, Obviously, we are maximizing in both of these cases. This is a maximization problem. Max here also. So yeah, I hope you can clearly see the recurrence already. So let's see how to implement this one. Instead of implementing naively, because it's going to be exponential clearly, and I'm going to memorize directly. And if you want to memorize this one, we need a table, informally called a dynamic programming table or DP table. So that table is going to have, the solutions to all these instances, right? All these nodes in this tree we can see. So it's either F node or G node, right? Because either we are computing F or G, one of these two in this case. So and possible values of F are going to be from K is going to run from 0 to K, the first parameter here, and similarly n also is going to run from 0 to n. So roughly there are kn number of possible instances of function f. Similarly, approximately kn instances of g also. So we can have a table there, and then initialize with the base cases of when k equal to 0 and n equal to 0, and then just find f of k comma n, right? That should automatically do the job, right? So that way the time complexity is going to be big of kn, and space also big of kn. All right. So one more thing I'm doing here. So the function we want to implement here is here max profit k comma prices. So to start with, I'm basically trimming some prices. So what does this trimming prices mean? So I'm basically converting this array of prices to something else, right? What I'm trying to make here is, see, whenever we have some value, so let me just show the values in a graphical way. So suppose the first value is somewhere here, and second one here, third one here, and then fourth one again here, and fifth one here likewise. So it is like, it always goes this way, right? So sometime it drops and then goes this way. And if you see in this kind of, plot, there is no point in buying at any so there are these points called minima and maxima. So these points are called minima points, and these are maxima points, right? Minima point, maxima point. So they're all alternate clearly here. So there is no point in actually buying or selling on any other points. And we we should only buy on minima points and sell only on maxima points, not necessarily the immediate maximum. What if there is only k equal to 1, right? And there is a high maxima here. You may want to buy at some lowest minima and then sell at highest maxima there, right? So that's a obviously maxima should be after this minima in this case. So but yeah, what we are going to buy on minima points and then sell on maxima points. So that's why any other points in between are useless to us, so we can trim them off, right? And also, if there is if the whole thing starts with a maxima, and then we have first maxima and then minima here, so the first maxima is useless. We always starts with the minima because we cannot sell and to start with, right? We got to buy. So we can start with the first minima, and there is no point in having minima in the end because you don't want to sell at a lower price. So we can end with a maxima. So that's why I'm going to have a pair of minimas and maximas, which are always, like the pairs where n minima appears before maximum, right? So that's what I'm going to trim the whole array. So this is what I'm trying to do here. I get to the first minima in this loop, and after that, every time, so when I find the first minima, I don't obviously add anything else. So this loop actually figures out all those pair of minima maxima. So this loop actually just runs through if there is a series of increments, and then once we get a minima maxima, we are going to add both of them here as a pair, right? And if there is a drop, obviously I could have had another while loop for dropping here, but I didn't do that. So this increment actually does it, slowly, so that if there is a drop, that means if there is a descent, that goes slowly once in this outer while loop, right? So essentially, I'm going to have these pairs of minimum maxima, and that reduces my problem size, right? So that's what we have. And so now onwards, I don't have to care about the values I have lost, right? I can only solve for the problem I have at hand. So what I'm going to do here, as I told you earlier, I'm gonna reverse it because I'm solving for the reversed version of the prices. And if the number of elements are just 1 or 0, obviously we don't have to solve that. We cannot even buy and sell because we cannot even make a single transaction. So that's why I'm returning here. Actually, when we trim here, we are going to have even number of prices here in the new prices. So one is not a chance, but I just wrote it, right? So now again, k also could be a really huge value, but I'm not interested in higher k value because suppose if there are like n number of entries in the prices, so we cannot make more than n by 2 number of transactions because a transaction need 2 days, right? And they're not overlapping. So if k is more than n by 2, I don't need that value. So I can always bring it down to just n by 2, so that I can save some space in whenever I'm using this kind of things. All right. So that's what we have here. So I'm having these DP tables, both of them, table F and table G. Both of them has this size of k plus 1 rows and then n plus 1 columns, because it has to run from 0 to k and then 0 to n. So after that, this loop is just initializing with the base cases because this is memoization, right? So I want to initialize the base cases so that I can solve for the rest, right? For all other values, I'm initializing with int min. Int min indicates it is not yet solved, right? And so that's all I want to solve is f of k comma n, and these are the tables we need to carry on. So now let's look at how does the function f look like. So function f has k comma n. And if it is already solved, I'm going to return because this is how memoization works. Otherwise, I need to explore the with and without path. So without path is going to be f of k comma n minus 1, right? And with path is g of k comma n minus 1 minus the prices of that day, right? Which is at n minus 1th location because it is zero best index. Now I'm going to take the max of these two because I'm maximizing and storing in the table and returning from the table. So this is memoization simple, right? And g function in the similar way, that's also g of k comma n. And if it is already solved, I'm going to return it. If it is not yet solved, I'm going to solve. Again, with and without. Without essentially is don't sell, and with is sell. So if I don't sell, it is g of k comma n minus 1. But if we sell on that day, we are going to get this kind of a gain of prices of n. That's why I'm adding this. And also we are solving for another problem called f of k minus 1 comma n minus 1, right? Take the max of these two possibilities and store it in the table and return from the table. So memoization works nicely here, and it should work. All right. So it works for the cases. Yeah, it worked here, but I'm not going to run this one or submit this one. What I'm going to do is I'll quickly make it bottom up from top down. So bottom up code, let me show that code here. So otherwise, yeah, trimming is still done. No changes there. So up to this point, there are no changes. Up to line number 43, there are no changes because we still need the table and go with that. But after that, what we need is, I'm going to initialize the base cases here first. I think this is also common there. But yeah, I'm not initializing with int min here because I don't want to spend time in initialization also, because I don't need to, because it's all about base cases here, and any other non-base cases are going to be computed right directly. So we don't need to access them. So if you go through here, I'm going from I equal to 1 to k, and then j equal to 1 to n, because zeros are base cases, and it should go up to k and up to n. And these are the two recurrences we have, right? So the recurrences are f of k comma n, I comma j is essentially k comma n, is max of f of k comma n minus 1 and g of k comma n minus 1 minus prices of that day. Right. Similarly, G also we already have it, right? So both of them are solved that way. So once we come out of this one, f of k comma n is going to have the answer. So this is exactly that. And then how did I figure out the bottom of piece? I looked at the dependencies between f of k comma n and g of k comma n, and this order is supported. It is essentially what is called topological order, and that's how bottom up approach works, right? There are multiple ways of doing this one, but I chose this, right? And this should also work in the same way. Maybe it's a little faster because we are going to avoid a lot of function calls, right? So let's see. Yeah, it worked for the sample test case here. Let me submit and see if it works. Right, it accepted, right? Maybe it takes a little more time. So now I have one more possibility of improving the performance a little bit, mostly space related performance. So let's see how much space this takes, and then we can compare the performances there. Here we took 964 milliseconds and 223 MB, right? I think both of them are on the higher side. Let's try the other method. The other method here is, instead of using the whole table of all the rows, we don't need all the rows. If you observe the recurrence, we only access previous row in F and previous column in both. So that's why we don't need the whole row. And for F, we need both previous row and current row. For G, we don't even need the previous row because we don't access the previous column at all. Sorry, previous row at all. We access just the previous column in G. So that's why what I did here is, for G table, I just have one row, and for F table, I have G two rows here, right? So I'm initializing both F and G here because they are the first rows, and we don't need to initialize the column because that's not there at all, right? Just that for the second row of F table, I need to initialize 0 for the first value because that is the column, zeroth column. Now this loop is similar. The code is not different from previous one, except that whenever I'm accessing a row of F, I'm accessing based on whether it is odd or even. Because when I is odd, the even row is the previous row, and when I is even, the previous row is odd row. And this actually clearly makes it 0 or 1, right? 0. When I bitwise AND with 1, it's always 0 or 1. So that's how whenever I'm accessing table F, I'm just using bitwise AND. So look at this, there are multiple places. So here I'm accessing the previous row. This is the only place that needs the previous row. That's why I'm having two rows. Otherwise, G never needs a previous row. That's why it's always previous column. I'm accessing in two different places here, but both of them are just previous column and they work nicely here. All right. So that's how I got it. And finally, I'm returning again based on whether K is odd or even. All right. So this should also work, and let's see how whether it improves a little bit, right? It accepted. Let's look at how good this is, right? So time wise, yeah, it's little better, but I don't know how much better it is. But look at the memory. Memory, it came down from 200 odd MB to just 12 MB. That means we saved a lot of space, right? But time wise, this is still probably on a little higher side. There must be some better methods than this, because look at this, my percentile is so low, right, at 16%, but it is accepted, right? So if you know any better methods than this, please let me know, and we can discuss that in the comments. If you have any questions, any comments, please put it down there. All right, otherwise I uh, uh, subscribe to the channel and then like this video, and also I have multiple playlists, and this video is going to go to both the playlists: October LeetCoding Challenge solutions, and also backtracking and dynamic programming concepts and solutions, right? So both of them, because it fits into both of them. All right. So yeah, please take a look at other videos and subscribe to the channel. Thanks for watching. Happy coding.